at least for two reasons. First, I have started a collaboration with Catania group of kilometer cube supernova neutrino detections. And second, just yesterday, as is shown here, we have an international release of the discovery of gravitational waves together with light, including gamma ray lines. So now, it is clear that the neutron star merger can produce gold, platinum, and rare earth elements. So having all these, very lucky events, we will now discuss the impact of nucleosynthesis on neutrino physics in neutron star mergers as well as supernovae. So one of the purposes of our science is to study the cosmic evolution. We are now here in 13.8 billion years from the beginning of the universe. And starting from a BBN, Big Bang nucleosynthesis, we have much of a nuclear reaction processes. For example, in the supernovae exploded already in the early galaxy from the very, very early history of the cosmic evolution. And quite recently, we have binary neutron star mergers or black holes. And all these are the places where we can find the elements. So today, we will discuss how to relate the neutrino physics, especially including the neutrino strange form physics with nucleosynthesis with this astrophysical site. And one question is, mergers, it's a very, very, interesting object. However, the merging time scale is at least 100 mega years. So this means the early galaxy, these have not contributed. So in our studies of nucleosynthesis, we should take account of this. Now here, please look at the right-hand side. Here we have information about observation of double pulsars. Double pulsars clearly indicate that we have object of both two neutron stars. And from the observed orbital eccentricity and orbital period, general relativity tells us at least 100 million years is required for them to merge. And from these pulsar observations, some of the pulsations would suggest us that 10 trillion years later from now, they will merge. We are now here, it is far future. But the point is, at least 100 million years is required. So, binary neutron star is very interesting, but could not contribute to the early galaxy. However, astronomers have already collected the R process elements, barium, europium, as a function of metallicity. And we have a metallicity time relations. So this metallicity minus 4, this means that 10 to the minus 4 times smaller ion relative to hydrogen, relative to solar, was observed in these stars. Extremely metal poor stars have already contained the much of our process elements. And supernova time scale is very short, can contribute. However, assuming a neutron star merger are process, it delays until metallicity minus 2 or 100 mega years, consistent with observational suggestions. So, generic difficulty of gravitational wave radiator of neutron star merger is this time scale delay problem. So we should anyhow explain first if the supernova can explain these very metal poor R process elements. So here we show the lineup of observed metallicity stars which contains much of our process elements. And as you know, these very extremely metal poor stars were born very early galaxies. However, their abundance, relative abundance pattern is very similar to the solar system abundance. This shows us that even in the very early generation of stars, or even in the present solar system, our process could occur in the very, very narrow conditions. So what is it? Only supernova can produce it, or we need some, for unknown mechanism, neutron star mergers in the galaxy too. So in order to under this thing, we first carried out our process nucleosynthesis calculation in the one of the supernova models, which is called the magnetohydrodynamic jet. And it started from proton-neutron alpha particles, and the explosion time scale is very short compared with the neutrino interaction time scale. Once the neutron-rich condition is created at the beginning of explosion, it is kept until the last time. So neutron condition can make much of our process elements. So asymmetric magnet hydrodynamic jet supernova can produce much of our process elements. However, for completeness, we have already calculated the neutron star merger process because we live now in a solar system. Solar system was born about 4.56 billion years from now, and there was enough time for neutron star mergers as well as supernova contribute to the solar system abundance. So again, in the binary neutron stars, after touching of explosional process, time scale of jet is so short, shorter than the time scale of neutrino interaction. Therefore, again, neutrino interaction do not disturb much about a neutron-rich condition. But the second interest is the neutron star merger can provide much of cold neutrons. Therefore, reaction process can easily reach the fission regions, and the fission recycling can make the process abundance in neutron storm mergers. But the point is, they could not produce a light element abundance including iron, carbon, and magnesium and others. Okay, having all these ingredients, we compare with astronomers' suggestion of universality. Again, let me say that these very metal postures born in the early galaxy are consistent with the solar system abundance. But now, theoretically, even without neutron star merger contributions, only a magnetodynamic jet supernova can explain the universality this well. So this is quite natural because in the early galaxy when these stars were born, there was short time for neutron star mergers to contribute. Therefore, this is a very, very happy situation. And this is the solar system abundance predictions compared with observations. In the early galaxies, only neutron-driven wind model and MHD jet supernova could contribute. But as the time passes by until the present time, as was discovered in the last August, neutron star merger can contribute to produce even the heavy R process elements. And here, by combining neutron-driven wind model, MHD jet supernovae, and neutron star mergers, we could explain the present-day solar system process abundance this well. And this is not an accident. We have evaluated in this way the event rate observed. For example, neutron-driven wind model occurred at least once or twice per century per galaxy. We adopted this observed event rate multiplied by the ejected R process abundance. Likewise, MHD jet supernova, whose progenitor was probably magnetar-like supernova, so its event is very, very small. So just a 3 or 1% multiplied by the ordinary supernova event rate can contribute to the MHD jet supernova. And if our understanding of a short duration gamma ray burst are the central engine of neutron star mergers, this is much rare event. But anyhow, having all these observed event rate multiplied by the produced R process elements, we could explain this contribution rate of a solar system R process abundance. So one conclusion is, in the early galaxy, we need only a supernovae because of the time scale. However, at the present time, neutron star merger can contribute. So we need both. So cosmic and chemical evolution from the beginning of the universe until the present time is the next target. So how is the neutrino interaction operating such kind of nuclear synthesis? So in order to understand the role of neutrinos, let's start our discussion from this part. This part of neutron star mergers and the MHD jet supernovae expansion time scale is so short compared with the neutrino interaction. So very fortunately or unfortunately, these are relatively free from neutrino nucleus interactions. However, as you see, the neutron-driven wind model of supernova can explode slowly. Therefore, this depends on the neutrino interaction very strongly. We should be careful about nucleosynthesis prediction. We should study not only MSW effect, but the coherent scattering of neutrino-neutrino interactions, and also the vacuum oscillations. All these oscillation stuff should be included. So unfortunately, we are still premature, theoretically, to know the real truth to compare with this observation. One fact is this. People have now jumped on neutron star mergers and MHD jet because of a heavy R process element. But the first peak elements are not fully understood yet. So what is needed? We would like to propose the neutrino process is very, very important. And it could be possible that we should need some new process assisted by neutrino oscillation effect. So my discussion in the following 5 minutes is this. Here we show the sketch of nucleosynthesis in supernova. Here we have proton-neutron star. Shock wave is around here because it is just 1 second. And we have discussed our process here. However, this could be affected strongly by the neutrino coherent corrective oscillations due to the coherent scatterings. We haven't yet included this effect. It is so difficult and subtle questions. So instead of our process, what kind of nuclei could show us the evidence of a neutrino-nucleus interactions? It would be probably the new P process nucleosynthesis, which could occur here after the corrective oscillation could occur. And we have almost consensus about a neutrino temperature hierarchy from a single supernova of neutrino-driven wave. Because of the structure of neutron star, nu E bar, and nu X, which is a representative of mu and tau neutrino and their antiparticles, have a temperature hierarchy. Therefore, mu and tau type neutrino have the largest energies compared with nu E or nu E bar. Neutron oscillations can change the flavors among these three. So now we should take account of these interactions very strictly. So what could be the signals? It is the new P process. And now we will show. Probably yesterday there was a hot discussion about this. We should know the corrective neutrino oscillation effect. It is a quantum many-body effect. And writing down the MSW one-body effect and the self-interaction, which is assumed to be coherent in the present understanding, Hamiltonian or Lagrangian are written clearly. However, it doesn't mean that it is easy to solve. Because if neutrinos is forming a lattice, like a spin lattice, it is easy. We know many absolutely soluble models. However, they are moving. 10 to the 49 neutrinos coming out from the supernova core can move. So momentum and position and 3 flavors per each neutrino should be included. So we take a mean field approximation. Still, in the mean field approximation, there was no exact solutions together with the nucleosynthetic evolution. So we have challenged this in order to find the signal of neutrino corrective oscillation in nucleosynthesis here. Okay, this is just a theoretical part, I skip it. And here we have one example. We assume both normal inverted unknown hierarchy and observed mixing angle and mass squared difference. And this is one example in the case of inverted mass hierarchy. At the surface of neutrino spheres, we have energetic mu and tau type neutrinos. But when it travels outward due to the corrective neutrino oscillation effect, there is a swapping between the energy. Mu and tau type neutrinos, it's swapped. it is not controllable at the moment theoretically. However, anyhow, at best, we have solved this by using a mean field approximation coupled with a nucleosynthetic code. The interesting one is the following. Here, as a function of radius from the center of a neutron star, without oscillation, with oscillation in the inverted and normal mass hierarchies, here we have the reaction rate coming from this rate. This nu bar bombarding on proton can produce a neutron. Very interestingly, because of the neutrino corrective oscillation, assuming a coherent interactions, we have here the continuous supply of neutrons. Therefore, once we have a proton-rich condition, neutron richness was broken, and which was the reason why people are jumping on the other object from supernova. But because of the corrective neutron oscillations, again, neutron is produced continuously in the outer distance. What would make some signals observations in nuclear synthesis? Here we show the new P process, which was first proposed by Carla Freirich a couple of years ago, and she pointed out that the proton-rich conditions, nickel-56, zinc, and germanium-64 are easily created. However, because of the neutrino interaction, this neutron can bypass this very slow beta decay. The NP reactions, strong NP reaction can make this part very rich, and therefore nucleosynthesis goes on. However, it's not enough. They ignored the correct neutrino oscillation due to the coherent scattering. So we included the correct neutrino oscillations, and please compare without and with neutrino corrective oscillations here. The difference is this. This bypassed by NP reactions, but in addition, neutron is continuously produced because of corrective oscillations, and this neutron can make a much heavier nuclei. And interestingly, from the protons rich side or N equals Z side, N gamma and NP reaction can make these elements. These could be supplying mass 100 nuclei, which has long been the mystery of the origin as a so-called P process elements since Babbage, Farlow, Hoyle. So we show here the resultant calculated result. Here we have so-called overproduction factors relative to solar, and these P nuclei relative to solar relative to iron. And no oscillation and inverted mass hierarchy, it is almost declining in abundance. However, in the case of normal mass hierarchy, this could be enhanced this much by 2 or 3 orders of magnitude here. And in this comparison, we just included iron production in the Newton-de Bon model. However, we know iron is produced in silicon burning outer layers. Therefore, by including all these production from a single episode of supernova, we estimated that this is a level of a solar system abundance comparable to this. So only with neutrino corrected oscillation included, these ruthenium, molybdenum elemental abundances are explained very well. So this is one consequence of the impact of a nucleosynthesis in associated with neutrino interactions. Okay, this is just for this one. However, there are many other nuclei to be affected by the neutrino interactions. They are, for example, niobium, technetium, tantalum, lanthanum, as well as boron and lithium. So very interestingly, in the inner regions of carbon-rich or oxygen neomagnesium layers, these nucleosyntheses are free from MSW effect. However, once MSW effect occurs, energetic neutrino comes out suddenly. Therefore, if you look at the lithium, barium, boron compared with these heavy nuclei, you could know the emissivity effect. So hopefully we will know the mass hierarchy in terms of nucleosynthesis. So in the last couple of minutes, let us discuss this. So first, tantalum and niobium, these have a very, very similar structures. We are now interested in this one and this one. And the P process and R process do not contribute because they are blocked from proton-rich side or neutron-rich side. So at the moment, some over S process and the strong flux of neutrino process can contribute to production of tantalum. Not only tantalum, but the niobium and others are consistently reproduced by including a neutrino oscillation, neutrino interactions. So this includes much of a nuclear reaction physics because as is famously known, tantalum 180 ground state decays in 8 hours. However, isomer has a long life, more than 10 to the 15 years. So what we have on Earth or in the universe as tantalum is this isomer. This is well deformed, but these are probably produced by way of neutrino interactions. But after explosive nucleosynthesis, they will just decay through the intermediate state population and depopulation to decay. So we should combine with nuclear structure coupled with dynamical evolution nucleosynthesis. We have done it by using Einstein AB theory. Einstein AB theory suggests as a population from this deformed isomer to the intermediate state to decouple or de-excite the ground state or vice versa. So we have done it, and we can now produce these elemental abundances consistently with a single set of supernova neutrino parameters. Now, let us compare with the light elements, which could be affected by the emissivity effect. This is the bottom of helium layer, and emissivity effect occurs here. High density resonance is located here. So suddenly, mu and tau type neutrino can change their flavors to electron type, and anti-electron type neutrino both are created to change the charged current interactions. We have adopted a supernova explosion model and neutrino oscillations and also the explosive nucleosynthesis code together to find this result. As a function of theta 1,3 mixing angle, we have the separation of predicted lithium to boron abundance as one example of neutrino process nucleosynthesis. Normal mass hierarchy is very separated from an inverted mass hierarchy or no-mixing case. And we know we have just narrow window of theta 1,3 in the last couple of years. Many world long baseline experiment determine theta 1,3. We can separate this. We compare with the observed cosmochemical observations of supernova grains to find that the lithium and boron purely coming from supernova explosions. And now compared with these 11 data, we conclude that the inverted mass hierarchy is statistically more probable. But we don't know. This depends on the accuracy of these data. So we should do more about the cosmogenic observations as well as astronomical observations to pin down the supernova nucleosynthesis, pure ones. Okay, now lastly, the time is almost up. Let me remind you, here are many nuclear experimentalists who play the game of neutrino interactions, weak interactions. So in our whole game of supernova nucleosynthesis or neutron star merger nucleosynthesis, neutrino nucleus interaction should be calculated by using a new generation of Hamiltonian and shell model or the QRPA. So there are only data points for carbon measured. So we calibrate our theoretical calculation to this unique measured cross sections and then apply to the other elemental neutrino nucleus interaction cross sections. This is really a challenge. But by using the hadronic charge exchange or leptonic or photonic induced reaction instead of neutrino beam experiment, which is still difficult at the moment for low energies, we could know the neutrino weak interaction rate in nucleus. And this would open the windows of cosmology and other physics. So please provide all these needed cross-sections which may be able to discriminate the mass neutrino hierarchies. Okay, now time is 0. Let me summarize my conclusion. First, we discuss our process. Our process elements in the early galaxy are predicted to be dominated by supernovae component without neutron star mergers. It is no doubt neutron star merger can make gold and other process elements. However, they have arrived later in a recent solar system epoch. So now, fortunately or unfortunately, still a neutrino signals was not detected in a neutron star merger event. Probably they form just after the merging the black hole. But a lot of questions are together with neutron star merger event. So it is the dawn of multi-messenger astrophysics, including gravitational wave, optical light, gamma ray line coming from nuclei elements, and also neutrinos. So we should do much more to study the neutrino interactions in these objects. And secondly, we discuss the R process first peak is only created in the neutrino-driven wind supernovae. Still, we have a lot of interesting questions to know. Really, our process is enough to explain the mass 100 peak. And here we propose that the P nuclei, which has not been resolved for more than 50 years, since Babbage Hoyle, it could be produced in a proton-rich neutron wind model with assistance of collective neutrino oscillations. So it is now more interesting to understand the whole understanding of heavy elements. We should study the neutrino interaction and also neutrino collective oscillations. And finally, this is quite important to connect nuclear experimentalists, theorists, and astronomers and astrophysicists. Thank you.